Hello and welcome back. This week it's going to be kind of a short one. I have a few additional things to finish up, things that we haven't covered yet. And then I want to do kind of a quick review because next week will be your second test. And the second test counts for much more than the first one did. So if you missed the first test, you can still pass this class. If you don't take the second test, there is just no way mathematically that you can get through this class with a passing grade. So even if you don't do great on that second test, take it. Don't let it go by, because if you do, you might as well just withdraw. And time for that, I don't know, that's running out. But so let me go back to Blackboard here. Let's share my screen here and turn me off. And let's see, go to the course I always go to, which is the morning, Tuesday or Monday morning one, doesn't matter. Under lessons, we were down here in Module 2. And in Module 2, we already went through the slides. We went through the additional slides. We saw a couple of videos on transformer operation. We looked at early ignition system operation. I'm going back to when they used to use points. We looked at the video on electronic ignition system operation, and we looked at a video on Hall effect sensors. So what's left here in Module 2 is the even more slide. So let me launch that. And some of this is kind of dated, this material, but let's just go through and, we'll use it to, so you can see the different types of systems that have been out there over the years and that are out there now. So first off, there's some terminology that I need to talk about. In 1996, the Society of Automotive Engineers, SAE International, came out with some new rules for the car makers. And prior to 96, any manufacturer could use whatever name they wanted for different parts of the car. So for example, if you were talking about the sensor in a vehicle that measures the temperature of the engine, General Motors called it a CTS, coolant temperature sensor. Ford called it an ECT, engine coolant temperature. If you were working in an independent shop, you had to be familiar with the terminology that all the different manufacturers were using for their hardware. So in 96, you can look it up, I believe it's SAE J1930. A lot of things happened to make it easier for independent repair shops to keep up. One thing was the common diagnostic connector, what we now know as the data link connector, that 16-pin connector that's always located in roughly the same location in the car, and it's the same shape, and several of the pins are standardized to have the exact same functionality. For example, pin 16 is always the 12-volt power for your scan tool. There are ground pins. And then some of the pins the manufacturers were free to do whatever they want with them. So there are still some differences, but it is a common data link connector. And what that allowed is for the kind of scan tools you see today, where you can just buy a cheap little code reader and it's going to have the right connector on it. And when you plug it in, it's going to be able to talk to the vehicle. So there's, commonality in the hardware and in the software, in the code format, and everything that's used to get diagnostic trouble codes and data out of a car. Prior to 96, every manufacturer did their own thing. You needed either multiple scan tools or a lot of different adapters for your scan tools. They may or may not be able to talk to a Honda or a Toyota. We're now pretty much one scan tool. It's kind of universal. Well, they did the same thing with terminology. So, give you an example. The correct SAE term for that thing that charges your battery is now generator. Even though we all know that they are alternators, generators were something that they had back in the 50s and put out direct current. Alternators were more efficient, but the official term is generator, even though it's actually an alternator. So we're talking about ignition systems. So let me tell you where that all factored into ignition systems. So this, I'm telling you, was called the Ford, come on, where are you? Ford DIS. Right? That was its initial name when it came out. And DIS stood for, write this down, it was, oh, I got to change that color, that's no good. That should be a little easier to see. Get rid of that, try again. Okay, DIS stood for distributorless ignition system. Yeah. And, you know, that was new back then, an ignition system without a distributor. And so now the J1930, the SAE terms, you have basically two types of ignition systems. You have DI. DI equals distributor ignition. So these are becoming rare, right? They have a distributor. And then EI. EI is, it stands for electronic ignition. Now this is really stupid because a lot of distributor systems from the mid-70s into the 90s, 2000s, even though they had a distributor, they were still electronic ignition systems. You've seen them in the shop. I showed you electronic distributors. So I hate this terminology. I hate that they call anything without a distributor electronic ignition. But these are the terms. So you've got DI and EI. So every time I show you, let me get rid of this. Every time I show you a slide for one of these ignition systems, you may notice that I have the initial term, so Ford DIS, and then the more modern term, what it was renamed to, the EI, low data rate. Right? So this thing used a Hall effect on the crankshaft, and then it used a separate sensor, what they call the cylinder ID sensor, cam sensor basically, to identify cylinder number one. So the crank sensor can tell you that the number one cylinder has reached top dead center, but what it can't tell you is, are we on the exhaust stroke or are we on the compression stroke? That's where the cam sensor comes in. If you have a waste spark system, which we've discussed in the past, we really don't care whether that number one cylinder is on the compression stroke or the exhaust stroke, right? We're going to fire the spark plugs regardless. So they're going to fire on both of those strokes. So it really makes no difference, and the cam sensor really isn't very important to the operation of the ignition system. In those systems, it's more likely they use the cam sensor to synchronize the fuel injectors so that it knows which fuel injector to fire on the intake stroke of that particular cylinder. Typically, as the air is flowing into the cylinder, the injector injects fuel into the incoming airstream. So they want to fire that on the intake stroke. But back to ignition. So these early distributorless ignition systems, they had a crank sensor and then they had a cam sensor. I was in a class in Detroit for Ford, and what they did is they pulled the plug on the cam sensor and they told us, go ahead and try to start the car. And there was about a 1 in 3 chance that this vehicle would start when you tried to start it. Because it had no cam sensor, it could tell when the cylinders had reached top dead center, No, actually, this crank sensor didn't even identify which cylinder was number one. So it just, every 120 degrees, it said, okay, another cylinder's at the top, another pair. And so without the cam sensor, no way of knowing which coil to fire. We know some cylinder is ready to fire, but we don't know which one, so, or which pair, which companions. So eventually the car started because it just happened to get it right. You shut it off, try again, it might start, it might not. So it needed the cam sensor to identify the number one cylinder. And it needed the crank sensor to identify that every 120 degrees. It was a 6-cylinder engine. So pulse come out of that, or a switch would come out of that Hall effect every 60 degrees, off, on. So it would turn on every 120, knowing that, hey, another cylinder pair is ready for its coil to fire. Which cylinder pair? Don't know. We need to look at the cam sensor for that to tell us which one is at top dead center. All right. So that one was early electronic ignition. They call it low data rate. And let's talk about that. If my crank sensor just has 3 big teeth on it, right? So a tooth starts, 60 degrees later the tooth ends, 60 degrees later the next tooth starts, 60 degrees later the next tooth ends. So there's only 6 updates. And in a 360 degree rotation, there's only 6 times when something happens on that Hall effect. Every time that tooth or blade beginning enters the sensor, or the end of it comes out of the sensor, that's going to be 60 degrees. Every 60 degrees, something will happen. So low data rate, yeah. The computer or the ignition module has no updates on crank position in those in between 60 degrees. All it knows is, hey, here we are now, and then it sees something 60 degrees later. Not a whole lot of information. So let's see if I have a picture of this. No, I don't. That's about all I want to talk about that. You can read this slide if you want. But I used to talk in great detail about this, but you're not going to see this system anymore. So the EDIS, Ford EDIS, and I'm just sticking with Ford for now. Again, 2 different names for it. The initial name, I'll just scribble this down on the screen here. The initial name was the electronic distributor list, ignition, my goodness, system. Right. Again, this naming was dumb because the system I just showed you was also electronic, so makes no sense. The new term, of course, is EI for electronic ignition, meaning no distributor, and then high data rate. Now, why is it high data rate? Get rid of these annotations here. So this thing used a completely different sensor. Let me flip ahead for a minute, because there's a picture. If you look at, there we go. This thing right here, specifically this trigger wheel, right? So let me get rid of those things. You'll notice if you counted these teeth right here, there would be 35 of them. But they're spaced every 10 degrees. What does that mean? That means there should be 36 of them. What they did was they put a tooth every 10 degrees, but then they had 1 tooth missing. And that missing tooth corresponded with top dead center on cylinder number 1. So now you don't need the cam sensor to tell you when cylinder number 1 is at top dead center. It's all off of the crank sensor, that missing tooth. So you'd have this sine wave. It was an AC, variable reluctance sensor we talked about in class, or magnetic pulse generator, or magnetic pickup. So you got that alternating current coming out of it. When it got to the missing tooth, there would be a gap in the signal, twice as long as the space between all the other teeth because of that missing tooth. And so that gap, that is not what I wanted to do. There we go. That gap, the missing tooth, is what would identify cylinder number 1. And so when it sees that missing tooth, okay, there's cylinder number 1, time to fire coil number 1. And, if it's a 4-cylinder engine, then I just count 18 teeth, fire the next coil. If it's a 6-cylinder engine, I just need 12 teeth, 120 degrees, fire the next coil. And if it's an 8, just 9 teeth later, I fire the next coil. So on a 4-cylinder, we're firing a coil every 180. On a 6-cylinder, we're firing it every 120 degrees. And on an 8-cylinder, we're firing a coil every 90. And we don't, as long as we get coil number 1 correct, when we see that missing tooth, and then just fire the coils in the correct order after that, we're going to be firing the right coil at the right time. It's a waste spark system, so we're firing that coil. 2 plugs are firing, and as you know from our discussion of waste spark, we don't care which one is on its compression stroke and which one's on its exhaust stroke. We just fire both plugs and have it over with. So this is way more similar to a modern automotive ignition system. The trigger wheel is a variable reluctance sensor. The reason we call it high data rate is now we know the crank position every 10 degrees, right? Realistically, we know it every 5 degrees because the beginning of a tooth, if there's a tooth every 10 degrees, from the beginning of a tooth to the end of the tooth is only 5 degrees. And then 5 degrees till the beginning of the next tooth. So, 72 times during the rotation of this wheel, the crank position is updated. Where with the old system, right, there were only 3 teeth, so 6 times per crankshaft rotation was the crank position updated to the ignition module or computer. The big change that happened now after this system came out is, let me see, this ignition module, right, just became part of the engine control computer. So instead of having a separate box, the crank sensor, instead of the wires going into an ignition module and then wires going from the ignition module to the computer, instead, this crank sensor feeds right into the computer. Whoops. 2 wires if it's a magnetic pickup, 3 if it's a Hall effect. And then the computer takes care of directly firing the coils. So we don't need this guy at all. It just went away completely. And that's about where we're at. That's kind of the current state of the art. The other change, of course, as you know, is on most vehicles the coil pack went away, and we have coil on plug. So the computer is just, controlling individual coils on top of each spark plug, and can fire them when the time is right. So I'll give you another example of a system that's out there. And again, this is a little bit older, but not so much different than the way systems work in 2020. If you remember last week, I was talking about, or it might even been 2 weeks ago, I was talking about how we have triggering devices, and that some vehicles, Ford early on used a Hall effect for their triggering device, and General Motors used a magnetic pickup or a variable reluctance sensor for its triggering device, and those were mounted in the distributor. And then when When we went distributorless, Ford stuck with that Hall effect thing down on, the crank sensor was a Hall effect. GM used a magnetic pickup on the crank. So you had these two different technologies accomplishing the same thing, just with different technology. Here's an example of a General Motors system where it uses both magnetic pickups and Hall effects. And you'll see that the Ford system I showed you before, right, is using this magnetic pickup, right? Just two wires, sends out an AC voltage. So it's not that manufacturers are locked into one particular type of crank sensor or cam sensor. So here's a General Motors system that has two crank sensors. Let's look at the diagram, and I know you may not be that familiar with I don't know how good you are with wiring diagrams, but let me just point out a few things here, right? So we have crankshaft position sensor A. Sensor A is a Hall effect. So they have it drawn here as switch contacts. So that's a little oversimplified because it's not, there are no moving parts in here, right? It's not a switch with moving switch contacts. But a Hall effect, as we talked about before, you have your 12-volt reference to it, right? So power. General Motors uses the term low reference when they talk about ground. So it's got power and ground. And this is the thing about a Hall effect. You supply power to the Hall effect. And then when the magnetic field hits it correctly, it acts like a closed switch. And so that 12 volts is fed, into the PCM. Get rid of all my scribbling here again and go back. So that's crank sensor A. It's a Hall effect. Crankshaft position sensor B right here, right? Notice that it's a little different technology. They're showing essentially a magnet and a coil of wire and only two wires, and that's the tip-off to me. The two wires, they're really kind of not well labeled because, as you know, one of these sensors puts out alternating current, which means it goes positive, negative, positive, negative. The low reference, I guess, it's just a comparison to what's coming in here. So if this is higher than that, then we have a positive, signal, and if it's lower, we have a negative signal. That's just basically the zero line. Let me get rid of that nonsense. So Hall effect here, magnetic pickup here, or variable reluctance sensor, whatever you want to call it. So this is switching on and off of direct current. This is alternating current feeding in. So the interesting thing, and we're going to forget the cam sensor for now. We're just going to concentrate on these two crank sensors, right? The crank sensor B here, on this particular engine, this trigger wheel is cast right into the crankshaft, and the sensor goes through a hole in the block and comes close to that wheel on the crankshaft. And it has, this is a 6-cylinder engine, it has a tooth or a notch every 60 degrees. So that is a low resolution, low data rate signal, right? And the ignition module here just takes that low resolution engine speed signal, passes it on to the PCM. Right, let me erase my stuff here, right? So it's just basically feeds it on through. So can the engine run off of that low resolution signal? Sure it can, How does it know cylinder number one? Well, one of the notches on this wheel is a double notch. So every 60 degrees you have a notch, but then where the number one cylinder is, 10 degrees off of that notch is a second notch. So when it sees that double pulse, oh, that's cylinder 1, right? So I know where cylinder 1 is, and on this particular ignition system, it was waste spark. So again, we don't care what stroke it's on, compression or exhaust. We're just going to fire the coil. So really, this is enough for the ignition system to work, right? This sensor here. But when you have low resolution signals like that, things like misfire detection are a lot harder to implement. And misfire detection is definitely a requirement since OBD2. So misfire detection counts on being able to measure how much each combustion event accelerates the crank, and it should all be equally if the engine's running smooth. And so the more updates we have on crank position, the more tightly we can monitor that. And what the official, description of the system, it says that it gives you enhanced smoothness, and I've never really understood exactly how it does that, having a second crank position sensor. But this one has a lot more teeth. There are 24, I believe it's called the 24X. So you've got the 7X signal here, which means there's an update 7 times per crankshaft revolution. This is the 24X signal, so there's an update more frequently. Let's go back to here. 24 times per engine revolution, right? So what does this thing here do for us? The camshaft position sensor? Really, as far as the ignition system operation, nothing. But again, like I said, the fuel injectors are sequential. In other words, they fire in the firing order of the engine on each intake stroke. So the cam allows this computer, the PCM, right, because that's responsible for firing the injectors. It allows the PCM to know what stroke we're on, where the ignition system doesn't really care. So here's another thing, that this system is a little outdated because it has an ignition control module. And like all of these older systems that have ignition control modules, there is some sort of communication between the ICM and the PCM. And so here's a timing signal, right? And here's timing control. So the PCM is really responsible for deciding when to fire the coils. So this timing signal right here, this is going to tell the ignition control module when to fire the coils, right? And then it's got control of the coils. This timing control can turn that off. It can basically make this wire useless. And when it does that, then the ignition control module is in charge and it fires the coils, but with no spark advance. It just fires them at base timing. So 2020 now, what do? We get rid of the ignition control module, and here's the ICM, right? They took it and they basically put that functionality right inside the PCM. Get rid of this stuff. Here's something we haven't really talked about. The NOx sensor. Some of you have had NOx sensor codes out in the shop. Somebody did, I don't remember exactly who. So what does the NOx sensor do for us? We're going to talk a little bit more, I guess, about spark timing. And the NOx sensor, we know from earlier lessons that if we over advance the timing, we get what's called spark knock, detonation. And if we get detonation, we lose power and we do damage to the engine. So what increases the likelihood of spark knock? High compression, high combustion chamber temperatures, the wrong octane fuel. So if our fuel octane is too low, it's more likely to explode. So octane is basically anti-knock. But even with using the correct octane, these ignition systems and powertrain control modules they have an objective, and the objective is to maximize fuel economy. So something I should say, let's find a spot to write here, up at the top, I guess. So advanced timing equals two things. It gives you better fuel economy and more power. Right? So it's advantageous to advance the ignition timing as much as possible. In the old days, when computers weren't so sophisticated or were not in control of things, it was kind of a, I don't want to say crapshoot or a gamble, but it was necessary to kind of play it safe because, right? Let me just say, over advanced timing equals detonation, possible engine damage, right? And loss of power. And if you lose power, you're going to lose fuel economy. So it's really a balancing act. We want to advance the timing as much as possible, but if we go too far, it's going to be really bad. So this is where the NOx sensor comes in. So our NOx sensor down here, right, is feeding a signal into the powertrain control module. So what this allows is it allows the PCM to push the limits on timing advance to right up to the point where the engine begins to knock, begins to detonate. And how does it know the engine's beginning to detonate? Well, it sees a signal from the NOx sensor. So then it can back the ignition timing off just a little bit. And then start pushing it again. And so what we have is we have this ignition timing operating at the very, very upper limits of what we can get away with. So that's going to maximize our power and fuel economy. And the NOx sensor is going to keep us from going too far. So if there's a failure of the NOx sensor, the PCM is going to go back into a much more conservative or safe timing profile. That's going to cost us, you would think NOx sensor, oh, no big deal, you know. If it knows the NOx sensor is not working, then it can't push the limits on ignition timing advance. And so we're going to lose power, we're going to lose fuel economy a little bit because of a bad NOx sensor. It's funny how all these systems work together. And, you know, if one thing goes bad, it can have effects other places. NOx sensor is one of those things. And what it is, I should probably find a video on how NOx sensors work, but they call it a tuned accelerometer. It is, there's a crystal in there, some designs, and at the same frequency, the same vibration frequency that detonation or engine knock puts out, that crystal, when it vibrates at that frequency, it puts out a small voltage. So I think in the one lab, when I was out, my substitute actually showed you how tapping the engine with a hammer can fool that NOx sensor. And if you're watching the spark advance and you tap the engine with a hammer, you can see the spark retard. In other words, we have less advance after hitting the engine with that hammer, because that causes the NOx sensor to vibrate. That causes the PCM to think that the engine is knocking, and its response to that is to decrease the timing advance. Okay, as long as I'm on that subject, right? Yeah. Let's talk a little bit more about octane. Start my video up again here, right? And just to wrap things up, I think I'll do a more complete discussion of fuel octane, or maybe in fuel and emissions you'll get it. Let me find out from the fuel and emissions teacher how much information you're going to get on octane and fuel. But there's the impression around there that high octane fuel has more energy in it, it's more powerful, or that it's cleaner, somehow has more detergents in it. I actually saw a sign at a gas station a few years ago, and it said, "Drive your engine clean." Big old sign, "Drive your engine clean, use our premium unleaded." And I kind of chuckled because octane and detergents and fuel are unrelated. You know, you can have 87 octane fuel with a good detergent package, and that's going to keep your fuel injectors clean every bit as well as 93 octane will. So what does octane do for us? So the thing with, or another misconception is, well, higher octane fuel is going to give me better performance. That's not so cut and dried. So let me explain how. If I have a car that has been engineered and designed to run on 87 octane unleaded fuel, and you put a higher octane fuel in it, the only thing that could possibly happen is maybe the when it's advancing the spark, the knock sensor doesn't go off quite so soon, so maybe we run at a little bit higher spark advance. That's questionable. So will we really get any more power? I don't know. But the other problem with higher octane fuel is it has a lower volatility, and so a bulletin actually came out years ago, and I think it was Ford, it might have been GM, anyhow, it doesn't matter. And they were running into some hard starting problems on cold engines, and the problem turned out to be that people were taking a car designed to run on 87 octane, and they were putting a higher octane fuel in, which didn't vaporize as easily, and so they weren't getting enough fuel vapor in the cylinders to get it started on a cold day. Kind of weird. So what happens if you have a car that's designed to run on 91, 93 octane fuel and you put 87 in it? If the vehicle didn't have knock sensors, there's quite a possibility that you could do engine damage, because that lower octane fuel is going to detonate a lot easier than the higher octane. So it could be bad. If the vehicle does have knock sensors, what's going to happen? I'm sure after what I told you, you can guess, right? The knock sensor is going to go off, right, when the thing starts knocking. It's not like an alarm. I mean, it's going to start generating a signal. The computer is going to see that knock signal, and it's going to retard the ignition timing, and we will lose some power and fuel economy because of that, because we're running a fuel that detonates too easily. So what am I trying to tell you? What I'm trying to tell you is vehicles have been designed for a certain fuel octane, and your absolute best bet is to put that fuel octane in it. Because if you're using driving a car that takes 87 octane, I don't know if you've looked at the prices at the pump lately, but if you put 91 octane in that car, you're paying a lot more per gallon of gas for that, and you're really not getting anything out of it. Because the car is designed, it's optimized for 87 octane. If you're driving a car that calls for 91 or 93 octane, then you put 87 in it. Worst case, you're going to do engine damage. More likely, with modern controls, the knock sensor is going to cause the computer to retard the spark, and you're going to lose performance and fuel economy because of that. I know airplane piston engines, they run 100 octane, low lead, so they still have lead in them a little bit, and 100 octane. And that's because they don't control the ignition. The ignition timing is fixed. There's no spark advance. So that's a little different situation. But in a modern car, the computer is controlling spark advance. The knock sensor is providing feedback to that computer. If it's over advanced or for some other reason we're knocking, one thing it can do about it is retard the ignition timing. So even if timing isn't the cause, or fuel isn't the cause of the knock, let's say we're overheating and that's causing the knock, retarding the timing will still help mitigate that problem, help it go away. Okay, I think that's about all I got for now. So this week, no test, right? So no test today. Next Monday, I will be posting the next test. I'll email you about it. I'll tell you what to expect on it. And that's worth 35% of your grade. So if you blow that one off, you're done. There's, really nothing I can do for you in that case. So if you're having technical problems for some reason you can't get to the test, you better get a hold of me and let's get those resolved before the test goes away. You know that, when I post a test or a quiz, it's going to be visible for a certain amount of time and then it's going to vanish and you'll never see it again. So if you don't do it while it's available to you, you won't be able to do it later. And you might as well withdraw, right? And I don't want to see that happen to anybody. So stay on top of your emails. Make sure you watch these videos. Everything on these tests comes from the stuff I'm talking about here on the videos and comes from the slides and the videos that I've posted on Blackboard for you to watch. I'll see you in lab this week.